In this video, we're going to talk about type 2 errors in hypothesis testing. And to remind you, type 2 error is when we fail to reject the null hypothesis, but the null hypothesis was false, right? And if you remember, type 1 error was different. And type 1 error is probability of rejecting the null hypothesis when the null hypothesis is true. And we explicitly control the probability of type 1 error by setting up the alpha of our test ourselves, right? We start the test with some alpha level, 0.01, 0.05, some values within 0.001 to 0.1. So we control the probability of type 1 error, but we really do not control the probability of type 2 error. Type 2 error depends on one important factor: how false or how much the null hypothesis is false. Because let me remind you, beta, probability of type 2 error, is probability of failing to reject H naught when H naught is false. The null hypothesis test on the mean is mu equals to some value that we call it mu naught. If that is a false hypothesis, probability of failing to reject it is called beta. So it really depends on how much it is false, how much this is false. And when we say how much, we mean that this hypothesis that we're making, right, how much is it off from the true population mean? In the previous example, the bottles in the bottle company, our test was on 12.2, right? And 12.2 is our hypothesized value. That is probably not the exact population mean. It is off, but how much is off, right? And that is a very critical point in calculating beta. So type 2 error depends on how much the null hypothesis is false, and we call it delta. And as you can see from here, delta is mu, which is the true population mean, minus mu naught, hypothesized mean. So let me reiterate that. Mu is the true population mean that we don't know about. Mu naught is hypothesized mean. The difference is called delta, and that delta determines probability of type 2 error, beta, and you'll see how. Here's how we calculate beta. And depends on what type of test we're looking at, one-sided of more than or less than or two-sided. These are formulas to calculate beta. And in all those formulas, you see that it really depends on the value of delta. All the other parameters you're familiar with. It's the alpha of the test, it is the standard deviation, sample size, and so forth. This is how we calculate beta. Beta is probability of failing to reject H naught when or given that H naught is false. And this is not a good thing, is an error. But what is 1 minus beta? Because beta is a probability, is between 0 and 1. But what is 1 minus beta? Is a complement of this probability right here. A complement of this probability will be probability of rejecting H naught when H naught is false. And that is a good thing, right? That's why 1 minus beta is called power of the test. 1 minus beta is called power of the test. And this is what this is about. If the null hypothesis is false and we do not make a type 2 error, then the test was a success, which is the 1 minus beta power of the test. So probability of type 2 error, we want to minimize that as much as possible, which will maximize the power of the test as much as possible. Beta is probability of type 2 error, and we want to minimize that. So let's take a look at one example here. It's the continuation of the GPA example that we had. And in that example, we hypothesized that the average GPA of students is 3.0. And the alternative hypothesis was mu is not equal to 3.0. So it's a two-sided test. It's a two-sided test. And standard deviation is 0.5. That is the standard deviation of GPA values in the university. Sample size that we take is 25. The test stat is calculated as 1.8. And the alpha of the test is 0.05. Now, in part A says if mu is equal to 3.2, what does that mean? That means that if the true average GPA of the university, if the true population mean is 3.2, okay, going back to here, 3.2 is this, mu. If the true population mean is 3.2, what is the type 2 error probability for this test? Well, first of all, this is a two-sided test. So going back here, this is how we calculate beta, right? Beta is equal to probability of z between negative z of alpha over 2, that is 0.025, minus delta times square root of n, that is 25 here, over sigma, that is 0.5, that is the standard deviation. And on the other side, we have z of 0.025 alpha over 2 minus same thing, delta square root of 25 over 0.5. Now, what is the delta here? Right? What is delta that we need to put here? Well, delta is based on the information given in part A. Part A says if the true population mean is 3.2, that means delta is mu minus mu naught, so 3.2 minus 3.0. That is mu naught. That is your hypothesized value. So 0.2. So I'm going to replace delta with 0.2. Okay. So 0.2 here, 0.2 here. And these z values, z of, we know that from before, z of 0.025, that is 1.96. That's from the table. So if we replace 1.96 here and 1.96 here and calculate these two parts, we'll get to probability of z between negative 3.96 and negative 0.04. How do we calculate that? You remember from before, we need to split that to two cumulative probabilities, probability of z less than negative 0.04 minus probability of z less than negative 3.96. And then these two probabilities need to be read from the table. The first one, probability of z less than negative 0.04, 0.0 and negative 0.04, that is the probability, 0.484, okay? So here, this probability is 0.484. What is this probability? Probability of z less than negative 3.96. You can double check that in the table, but that is very close to zero. That is way to the left of normal distribution, and z less than that is essentially zero. So the probability is 0.484. What is that? That is beta, probability of type 2 error. There is 48% chance that we do the type 2 error in this test, which is pretty high. Now, part B says if mu is 2.68, what is the type 2 probability for this test? Well, now this is a new population mean. So what we need to do is everything stays the same except there's going to be a new delta, mu minus mu naught, in this case 2.68 minus 3.0, which is negative 0.32, right? Now I have to change 0.2 with negative 0.32, negative 0.32. That will change these values to 1.24, 5.16, 5.16 here, 1.24 here, and the new beta is 1 minus 1.24. You got to read that from the table. Probability of z less than 1.24, if you read that from the table, is 0.893. So that will give us 0.107, so about 10%. So for part B, beta is 0.107, while for part A, beta was 0.484. So the beta went down if the true population mean is 2.68. And that makes sense because if the true population mean is way less than what we are hypothesizing, it has less chance that we make an error, because our sample is going to represent that, and that's why beta went down. Part C says if mu is equal to 2.68, what is the power of the test? Well, when beta is 0.107, power of the test is 1 minus beta, that is 0.89. That is power of the test, 89%.